Our next presenter is a master's student in entomology from the state of Maryland. He has quite the journey. A Marine Corps veteran and former EMT, he earned his degree in biological sciences from North Carolina State University. His passion for field research led him to work on a sea turtle project in Antigua and with Connecticut's Inland Fisheries Division. But it was during this time at the USDA's Plum Island Animal Disease Center that his interest in entomology truly took off. Now his research focuses on arthropods like ticks and mosquitoes that transmit diseases. Outside of research, he enjoys reading, exploring local restaurants and breweries with his wife and son. But the son really likes the brewery part. And he's trying to make an honest attempt at playing the guitar. Would you please welcome our next presenter, Joshua Jackson.
Check. Tick-borne diseases pose a significant threat to human and animal health here in Kansas and indeed around the world. I know from personal experience. As a kid, I was playing in the woods when I was bit by a tick infected with the Borrelia pathogen, which causes Lyme disease. I didn't realize anything was wrong until weeks later when my joints started swelling and I developed a fever. Quick trip to the hospital to drain the fluid from my knees, antibiotics. 6 months of doctor's visits later, I was able to clear the infection. But still, the experience was extremely unpleasant. That was over 20 years ago, and to this day, one of our best defenses against Lyme and other tick-borne diseases is to find where the infected ticks are so we can reduce our chances of coming into contact with them. We do this through a process called surveillance. Tick-borne disease surveillance involves collecting ticks from the environment and then molecularly testing them to determine what percentage are carrying dangerous pathogens. It's an accurate but expensive and time-consuming process, and overwhelmed diagnostic labs can sometimes take months to produce results. But what if we could streamline and speed up that process by quickly identifying if a tick's infected simply by scanning it? Previous work in other labs has shown that infrared spectroscopy, which involves shooting an infrared laser at a specimen and reading the pattern of light that gets reflected back, coupled with advances in artificial intelligence and machine learning, can diagnostically identify certain pathogen infections, such as Zika and malaria, in mosquitoes. The idea behind the technology is this. Biochemical bonds within an organism will reflect infrared light back at certain wavelengths. An infection in that organism can cause some chemical changes that will shift the way that light gets reflected, which we can then analyze with AI. We're hoping to be the first to adapt this technique to work in ticks. To do that, I will use an infrared spectrometer to scan healthy, uninfected, colony-grown ticks as controls, and then use a trained AI classification algorithm to compare those scans with the scans of ticks infected with various pathogens, viruses, bacteria, parasites, and the like, to see if we can differentiate between the infected and the uninfected individuals. Ultimately, the goal is to improve surveillance. By rapidly identifying a tick's infection status, we can reduce overall costs and increase the types of surveillance that can be done to keep our communities safe. With incidents of Lyme and other tick-borne diseases on the rise, it is our hope that this technology can help prevent others from going through what I went through all those years ago. Thank you.